Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And in this video, we're going to continue forward with our introduction to derivatives. You should have just watched the video series on the derivative at a point, or rates of change and derivatives. In that video, you would have learned that derivatives are the slopes of tangent lines to a curve at a point, and you'd also have learned the definition of a derivative at a point. In this video, we're going to talk about the derivative just as a function, which is slightly different than the derivative at a point. Remember, the derivative at a point looked, actually definition-wise, just like this, with the exception that these x's were actually a's. So it's a derivative at a point a is equal to the limit as h approaches 0 of the function evaluated at a plus h minus the function evaluated at a, and then that is all divided by h. And so we now just make that a general and call it x. That's really the only difference between the derivative as a function and the derivative at a point. If I tell you that f prime of x is the derivative of our function f of x, that means that wherever you are looking for the slopes of tangent lines for our function, we could trade that thought out for the derivative of the function. That will always tell us the slope of the tangent line at any point that we can plug in, as long as that limit exists. And that's a critical statement. That limit must exist. And there are often times when it will not. So a couple points to take away from this. It's somewhat obvious, but the derivative is a limit. So you're looking at things getting infinitesimally close to one another when you're talking about a derivative. Now, rather than belabor this issue and just talk about just this, let's go ahead and use it in an example, and then mention a theorem that's kind of important for us. So here we're asked to find the derivative and state the domain of that function and the domain of the derivative itself. And the function is given there. It's a rational function, probably one of the more popular styles of functions when you're initially playing with derivatives. So remember, the definition of the derivative as a function is as follows. Notice that I replaced the x's with t's because this is a function of time, not a function of x. So let's go ahead and replace our function values there. So we have the limit as h tends to 0. We'll need a bigger fraction bar here. That denominator is still an h. And let's go ahead and plug in the t plus h into our function f here. So this will be 3 times the quantity t plus h minus 1 over 5 times the quantity t plus h plus 3. That's f of t plus h. And then we're going to subtract from that f of t. I do want to again mention, because I'm seeing this as I'm grading things in my courses, and I've seen this for years as well, that students still make the mistake. If I ask what's f of, actually I'll write this in red because it's a warning. F of t plus h is not f of t and then plus h. That's a rookie move. It's, in my opinion, that's a bad move from 3 courses ago that should have been cleaned up. Your previous instructor should have caught that and weeded that out of your math bad box. If you make that mistake in a calculus class, it really does destroy an entire problem. There's no credit that can be given. So just as a heads up, so as an example, in this case, I will often see students who want to write what f of t plus h is like that, but what they end up writing instead is f of t like this, and then plus h. Immediately when I see something like that, I just give 0 credit, because that just tells me that you're in the wrong course. So make sure, and you're in the wrong course because you're two things. You're missing that skill, and I've told you not to make that mistake and you're still making it. So if I warn you about something, just be very aware. If I warn you about something and you're a student of mine and I say, this is a very common mistake, you should no longer be making this mistake. And if you make it, well, then you don't get credit. That's just like if somebody did this. Oh, a plus b squared is equal to a squared plus b squared. Again, there would be no credit given because that is an Algebra 1 mistake. These two are not the same. So just be hyper aware of your weaknesses. Make a list of common mistakes as you see yourself making them, and just make that list off the side and put that in red and say, never make these mistakes. Anyhow, that's a little diatribe that I go on every once in a while. All right, going back to this guy right here. Multiply numerator and denominator by the LCD. And you should know how to do this. So I'm just going to quickly do this here. I'm just going to say LCD to both numerator and denominator. Again, so many mistakes that can be made because of algebra. As I've mentioned before, in calculus, actually what kills a grade is not calculus, it's algebra. It's people who have very weak algebra skills or just simply misrecall things. So if you're one of those individuals that just has a bunch of holes in your algebra, you have to be very, very careful with your mathematics and always check what you're doing. Rushing through and doing something without checking your work. I'm writing and talking at the same time, so I'm sorry if I'm sounding weird. But rushing through and not checking your work is indicative of somebody who's going to make mistakes. So always slow down, take your time, make sure that you're doing the right thing. Notice here that I am not only multiplying out that numerator or distributing the LCD through the numerator, but you also attach the LCD to the denominator. So this is yet another issue that I will see, that people forget to put the LCD in the denominator as well. So just be very aware. Actually, I should write that as a warning. So that's, you can see actually why calculus is a little bit tough for students, is because there's so many different tripping points. Each of these is like a deadly tripping point within a problem. And if you have a very solid algebra background, then you don't make these mistakes. However, if you have weaknesses, they get found very quickly in calculus, very, very quickly. The next thing is not the next warning I'm going to give you is not actually something from your prerequisite courses. It is something that's just kind of added here. So when students do this mistake in a calculus class, I'm more forgiving because I understand it's kind of a new idea. But the idea is this: once you get to this point with this fraction, there's a lot of cleanup. You can see there's a lot of cleanup that has to be done. The distributions in the numerator should not be an issue. You should be able to do that. But what I find that a lot of people love to do is they like to distribute out that denominator. There is actually no reason to distribute out the denominator, but it's very difficult for students to understand why. Because, well, they're distributing out the numerator, so why not the denominator? I don't blame them when they say that. Like, well, I've been taught for years to distribute, to factor, all this other fun stuff. Here's my rule of thumb. Why did you even bother multiplying numerator and denominator by the LCD? Just think about that for a second. Why did you spend the time right here multiplying numerator and denominator by the LCD? And if you think about that, the answer is really because you want to get rid of all those compound fractions in that numerator. You want all these fractions here to disappear. That's why you multiply both numerator and denominator by the LCD, is to kill off all those fractions. And so the place that was kind of the issue, which was that numerator, you're going to distribute your mathematics through in that space. But the denominator was never the issue. This h right here was never an issue. So don't bother distributing that. So again, when I get to this step right here, I'm only going to distribute this because that's where the issue occurred originally. And to drive the point home, suppose that, as an aside, you had maybe some, it doesn't really matter. Let's say it's the square root of x squared plus 1. Let's say that's a plus 1. And there was a minus x. And this is all over, I don't care, x minus 1. And x was approaching, I guess it'd have to be 0, 1? No, hold on. It doesn't really matter. Let's just say it's some limit. I was going to make it up. Okay, so I changed it slightly just so it will work. All right, so as x approaches 0, the numerator is going to approach 0, the denominator is going to approach 0, and you see there's an issue. Well, the very first algebraic thing you can do is multiply numerator and denominator by a conjugate of the numerator. So when you do that, because you're multiplying numerator and denominator by the conjugate of the numerator is the only piece you're going to actually distribute stuff out through. So I'm going to write conjugate here. And if you do the conjugate multiplication, and by the way, I'm not going to finish this problem out. I just made it up, and I don't think it actually is worthwhile. Or I think it's somewhat broken, in fact. So this would be x squared plus x minus x squared. And downstairs you'd have x times the square root of x squared plus x. That's supposed to be an x squared. And then plus x, which again causes a massive issue, but it doesn't really matter. Downstairs, I'm not going to multiply everything out. Why? Because by design, x squared cancels with x squared, and then x will go into this x. And I just have a 1 upstairs. And this limit, unfortunately, is still not worthwhile to talk about, but still, that doesn't matter. The most important piece there is that I didn't multiply out the denominator because that wasn't what I was multiplying against initially. Initially, I was trying to get rid of that conjugate or that difference of radicals. So I multiplied by its conjugate. That's why I distributed it. Downstairs, I didn't distribute it out because I knew something might cancel. So that is kind of the heads up, is when you're making your choice for what to distribute out and what to keep factored, really base your choice on where you made your decision or why you made your decision to multiply by what you did. Well, I made my decision to multiply top and bottom by the LCD so I can get rid of all these silly fractions in the numerator. Great. Then distribute out that numerator, but not the denominator. That's very long-winded. Sorry about that. All right, so let's go ahead and distribute out that numerator. It's the limit as h goes to 0. Again, we're just trying to find, as a recall, the derivative of this function. Normally, it would not take even a quarter of this time, but I'm trying to give you highlights of mistakes I'll commonly see. Distributing through, I get 15t squared plus 9t plus 15ht plus 9h minus 5t and then minus 3. Next little set of warnings. Be very careful about that negative sign, okay? 15t squared with a negative. Let's see, a 15ht with a negative. 9t with a negative. And then 5t, 5h, and a 3. And there we go. I just kind of filled in the rest, which I should have done from the get-go. But anyway, things will cancel. 15t squared will cancel with that negative 15t squared. Let's see, this 9t will cancel with that negative 9t. This positive 15ht will cancel with the negative 15ht. Let's see, negative 5t will cancel the positive 5t. The negative 3 will cancel the positive 3. And you can see all that you have left is 9h plus 5h. Very hard to see if you're not careful with your handwriting, but be clean and careful with your handwriting. You'll be fine. So we get a 14h all over that denominator, h 5t plus 5h plus 3, and then 5t plus 3. Again, not distributing out that denominator ends up being incredibly helpful because we could see these cancel cleanly. And at that point, once those cancel, ask yourself if you can use direct substitution. We couldn't use direct substitution up to this point because we would have been dividing by 0. But now, if you allow h to go to 0, this piece right here will go to 0, but everything else remains. You'll have a 5t plus 3 times a 5t plus 3 downstairs and a 14 upstairs. So via direct substitution, this will be 14 over the quantity 5t plus 3 and quantity squared. That is the derivative of our original function at any given point t. There is one exception. It will not exist at t equals negative 3/5, but that's okay. That's not in the domain of our function anyway. All right, so again, just the warnings I want to give here, right? So if you find that evaluating a function at t plus 8 is difficult, or t plus h is difficult, practice that skill because it's an unforgivable mistake if you can't do that. If you decide at some point to multiply numerator and denominator by the LCD, do not distribute where you didn't need to multiply. That sounds weird, but basically only distribute to kill things off, right? So I distribute the LCD to that numerator because I want to kill off the fractions, so you will continue that distribution in the numerator into the next step. But the denominator you leave alone because, well, there were no fractions down there to kill off, so you're just going to leave that denominator alone. That was just a bystander. Watch your multiplications. It's always critical to watch your multiplications here. Negatives can creep in all over the place. And then finally, when you use direct substitution, once you decide to, make sure you don't write your limit anymore. Once you have substituted in, there's no need to write the words limit or the word limit. Finally, I'm just going to showcase this. F prime at t is equal to 14 over the quantity 5t plus 3 and quantity squared. The reason why I want to showcase that is because if somebody said, hey, you know what? I have a function 3t minus 1 over 5t plus 3, and I need to know the slope of the tangent line, let's say at t equals 5. Well, that's easy. The slope of the tangent line at t equals 5 is f prime at 5. And I could just plug that in, right? 14 over the quantity 5 times 5 is 25 plus 3 is 28 squared. Now, I'm not saying that 28 squared is easy, but I'm telling you that everything else is pretty fine. So that's 156, I think. That's what that would turn into. I could be wrong about that, but I'm almost positive that's right. So anyhow, that's the slope of the tangent line at t equals 5. Now note, in this problem, we're asked to state the domain of the original function. Okay, well that's not too bad. The domain of the original function, you could see right up here, we could not have t equals negative 3/5. So, all right, I'll just state that. Scroll down here, and I'll say domain is negative infinity to negative 3/5, and then skip over and start on the other side of negative 3/5 and go to infinity. That's perfectly fine. And then we were asked, what is the domain of f prime? Well, the domain of f prime, if you look at f prime of t, which is right here, you could see it suffers from the same domain issue. In fact, the identically the same domain issue. But I do want to state here that that will not always be the case. The domains of f and f prime are related. I promise you that. They're totally related. But there's a very simple example to showcase what happens to the domain of f prime every once in a while. So rather than going to a theorem next, I'm going to go ahead and just create a sub-example right now. And I want us to investigate what we're going to state as a theorem right now. So let's go ahead and put in a little example here. And we're going to let g of x equal the square root of x. By the way, the domain of g is everything from 0 to infinity. You can plug 0 into that function, and you can plug any positive value as well. All right, g prime of x, well, that's equal to the limit as h tends to 0 of g of x plus h minus g of x all over h. That should not be difficult now. We have the definition of the derivative as a function. That's exactly what it is right there. So let's go ahead and plug in limit as h goes to 0. We'll plug in the x plus h into the square root minus the square root of x, and that's all over h. Oh, this is a great example because if you take a look at that, algebra before calculus, you cannot do a direct substitution. You get 0 over 0 here. So algebra before calculus, we will multiply both numerator and denominator by the conjugate. When you do that, you're multiplying the numerator and the denominator by the conjugate of the numerator because there's that difference of radicals there. So that's the part you're going to multiply out. The denominator is just the innocent bystander. And so it is going to just sit there and not distribute through. You'll just leave that alone. So let me, in fact, write that. The denominator will have an h times the quantity root x plus h, and then plus root x, but I'm not going to distribute through because that guy was not meant to be distributed through. The numerator was. When you multiply a difference of radicals by its conjugate, it will end up just getting rid of the radicals, x plus h minus x. And now we can kill off those matching x's, and you see you have h over h. So this ends up looking like, oops, black ink. The limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Allow h to go to 0 by direct substitution. You get 1 over root x plus root x, or 1 over 2 times the square root of x. And that is actually the derivative forever and ever of the square root, is 1 over 2 root x. The domain, this is the critical part, the domain of g prime is not the same as the domain of g. It's actually 0 to infinity, not including 0, because if you try to include 0, you'd have division by 0. And this is the critical part about domains of functions versus domains of their derivatives. The function is like the parent, and the derivative is like the child. Well, maybe that's the way I kind of think about it. And so all the qualities of the parent pass to that child, almost all of them. The child might have lost one or two. And in fact, that's what happens with derivatives. When you have a function with domain, let's say I, an interval I for its domain, the derivative of that function might lose a piece of that domain. And when it does, it will, more often than not, be an edge piece. So that gets us to our theorem that I kind of skipped to get to this problem. The domain of f prime, the derivative, is a subset of the domain of f. What I mean by a subset, well, if the domain of f was, let's say, negative infinity to infinity, all real numbers, the domain of f prime could be negative infinity all the way up to 0, union 0 to infinity. So it might like gain, or I should say lose a little bit of its domain. Now, I have to be honest with you, that specific example rarely, if ever, happens. But what is more likely to happen is the following. If you have the domain of your function being maybe -1 to 10, closed on both ends, the domain of f prime might turn into open at -1, still closed at 10, or it might turn into closed at -1 but open at 10, or it might turn into open at both ends, or it might actually just keep the original domain. So what I'm trying to drive home here is that when you're dealing with functions and their derivatives, the edges of the original function's domains might get lost when you take derivatives. You might shave off those edges, or that might still retain them. Rarely is it the case that you can take the derivative of a function and it loses something not on the edge. And I can't even think of an example right now like that. And because of that, I really am trying to think about it. Because of that, I'm just going to cross that out and just make sure that you know it might lose the edge points when you take the derivatives. And later on in this course, and again in Calc 2, when you try to go the other way, in other words, you're starting with a derivative and you're wondering, hey, what was that parent function? We call that integration. So when you go from the derivative to the parent function back to f there, it could be the case that you gain the edge points back. So taking derivatives, you could lose edge points, and going from a derivative back to its parents, you might gain the edges back. So that's a fun little fact about functions and their derivatives.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.